You flip a switch and the light turns on. It feels so simple that we stop thinking about it. But if you slow down and ask what actually happened in that instant, you run into a problem that should bother you. Because almost everyone is carrying around the wrong picture of what electricity is. And that wrong picture makes the real thing seem like magic. So let's do something uncomfortable. Let's take the picture apart. Let's rebuild electricity from the ground up, the way I like to do it, by refusing to accept words as explanations. Because if you tell me electrons flow, you haven't explained anything yet. That's like telling me water wets things. Yes. Fine. But how? What exactly is moving? And what exactly is causing what? Here's the misconception. Most people imagine electricity like water in a pipe. A battery is like a pump. A wire is like a hose. You push electrons through. They flow, and the bulb lights up. That picture feels natural because it matches something you already understand. Plumbing. But the plumbing picture has a fatal flaw. If electricity worked like water in a pipe, then when you flip the switch, you should have to wait, not much, maybe a tiny amount, but still, you should have to wait for the electrons to travel from the switch to the light bulb. So here's the first question that already tells you something is wrong. When you turn on a lamp on your desk, do electrons rush out of the wall and fly through the wire into the bulb at nearly the speed of light? No, they don't. In fact, in an ordinary copper wire, the electrons drift painfully slowly. I mean embarrassingly slowly. At typical household currents, the drift speed of electrons is on the order of millimeters per second. That's slower than an ant, sometimes slower than a crawling baby. So how in the world does the lamp turn on instantly? If the stuff of electricity moves that slowly, why does the effect happen so fast? This is where most explanations go off a cliff. They start waving hands and saying, well, it's complicated, or the electrons are already there, or the signal travels fast. But they don't tell you what the signal is. They don't tell you what is moving fast. They just change the words. So I want to do it properly. I want you to walk away with a picture you can actually imagine. Not a word. A picture. Let's start with the simplest thing. A wire. A wire is full of electrons. Not a few electrons. An insane number of them. In copper, there are roughly one free electron per atom participating in conduction. And atoms are packed so densely that if you could zoom into a millimeter of wire, you'd see a crowded ballroom of charges. So the wire is already full of movable charges. They're not coming from the battery, the way water comes from a pump. They are already inside the wire, all over it. Now add a battery. What does a battery do? A battery is a chemical machine that separates charge. It creates an imbalance. One end has a surplus of electrons and the other end has a deficit. That separation creates a difference in electric potential. You can think of it like height in a gravitational field. If you put a ball higher, it wants to roll down. If you separate charge, nature wants to undo it. But here's the important part. The battery doesn't have to push electrons through the whole circuit like a piston pushing water. What it does is set up conditions, an electric field that tells charges everywhere in the wire how to begin moving. And that telling happens fast, because the information about the field travels through the conductor at a significant fraction of the speed of light. Not the electron, the field, the arrangement, the pattern. So when you flip a switch, what changes first is not the arrival of new electrons at the bulb. What changes first is the electromagnetic field structure in the circuit, and that change propagates. Now the next thing people do is they hear electric field, and they think I'm dodging the explanation, like I've just replaced electricity with field and called it a day. No, we're going to make the field real. We're going to make it something you can picture. Let's do it with an analogy that's closer than plumbing. Imagine a long line of billiard balls touching each other in a straight line. You push the ball on one end. What happens? Does the far end wait for the pushed ball to travel all the way down the line? No. The motion travels as a compression wave. The last ball moves almost immediately, even though the individual balls barely move. This is not a perfect analogy, but it's closer to what's happening in a wire. The electrons drift slowly, but the influence, the push, the rearrangement propagates fast. And the reason it propagates fast is that the electromagnetic interaction doesn't require one electron to physically carry a packet of energy down the line like a truck delivering supplies. The energy and the momentum flow in the electromagnetic field around the wire. Yes, around it, not inside it, the way people imagine. This is one of the most shocking parts for people. They think the energy moves through the wire, but the wire is mainly a guide, a structure that shapes fields. The energy flows in the space around the conductors, carried by the electromagnetic field. There's even a precise way to describe this flow of energy, called the Poynting vector. But I don't want to drown you in symbols. I want you to feel the idea. Here's a circuit: battery, switch, bulb, wire. The moment you close the switch, charges slightly redistribute along the surface of the naticary wire. They barely move, a tiny shift. But that tiny shift sets up an electric field along the wire. And that field exists in the space around the wire too. Once the field is established, charges begin to drift. And the bulb responds because what makes a bulb glow is not electrons arriving. A bulb glows because electrons inside the filament collide with atoms. They jiggle the atoms. They heat the filament. And hot things glow. So the bulb lights because the field causes current in the filament immediately after the field structure reaches it. The bulb doesn't need fresh electrons from the battery. It needs the field that organizes motion of the electrons already there. Now, I can hear the next question. Wait. If electrons drift slowly, then what is current? Current is simply a measure of how much charge passes a cross-section per second. It doesn't require the charges to move fast. It requires there to be many charges moving, even if each moves a tiny distance. A crowded hallway with a slow shuffle can still move a huge number of people past a doorway. That's current. But again, if that's all there was, electricity would still feel like plumbing. So we need the deeper picture. The battery does work to separate charges. That energy is stored in the electric field configuration. When you complete the circuit, the field drives charges and energy flows through the field into the filament. Then the filament converts that energy to heat and light. So the energy is not a substance in the wire. It's not a fluid. It is the ability to do work carried by the field. Now let's make the misconception more obvious. Take a battery and a bulb. Connect them with very long wires, say 1 kilometer long. If electricity were literally electrons traveling from the battery to the bulb to deliver energy, then the bulb would turn on only after the electrons traveled that kilometer. But it doesn't. It turns on after the electromagnetic signal propagates again, some fraction of the speed of light, depending on the geometry. So the delay is tiny, but it exists. And if you build circuits with extremely long transmission lines, those delays become measurable and important. This is why radio frequency engineering exists. This is why high-speed computer design is hard. Because the field propagation is not instantaneous. It's fast, but it's finite. And that alone should convince you electricity isn't water. Because water in a pipe is almost incompressible and moves differently. The analogy breaks when you look closely. Let's go one layer deeper. People say electricity is electrons flowing. But electrons are not the only charges that can move. In electrolytes, ions move. In semiconductors, you can also think of holes, moving missing electrons, acting like positive charges. In plasmas, both ions and electrons move. So what is common? The common thing is not the electron. The common thing is charge and field. Electricity is the behavior of charges under electromagnetic fields. And the most practical way to understand circuits is to understand how charge distributions create fields and how fields guide motion. Now I want to make this feel less abstract. So let me ask you something. Have you ever gotten a static shock? You touch a doorknob and snap. What happened? Did a bunch of electrons flow like water? No, a very small amount of charge rearranged suddenly, causing a rapid change in field and a discharge through the air. The key is the field change and the breakdown of air as an insulator. That snap is a tiny lightning bolt, and lightning itself is a wonderful example because it forces you to confront the question, what is moving? Lightning isn't electrons traveling from cloud to ground like a stream. It's a growing conductive path through air, guided by electric fields where charges accelerate and collide, emitting light. Electricity in the wild is fields shaping motion. Now let's return to the everyday case, a power outlet. When you plug in a device, are electrons from the power station traveling into your house and into your appliance? Not in any direct, simple sense. The power grid is an alternating current system. Charges in the wires in your neighborhood are oscillating back and forth. They jiggle. They don't need to travel from the plant to your toaster. The energy is transmitted by the coordinated oscillation of fields and currents. Again, the wire is a guide, a field-shaping structure. So the big misconception is this. You imagine electricity as a thing that flows through the wire. But it isn't a thing. It's a process. It's a relationship between charges and fields. Now, at this point, someone always says, okay, fine, but what is the field? Good. That's the right question. And the honest answer is, a field is the bookkeeping device we invented because nature behaves as if space itself contains information about forces. If you place a charge somewhere, you change the conditions of space around it. Another charge placed nearby feels a force. We describe that with a field. But that doesn't make it imaginary. The field has energy. The field has momentum. The field can carry power. And it can exist even where there are no charges, electromagnetic waves, light, radio, microwaves. So if you want to stop thinking of electricity as water, here is the replacement picture. A circuit is not a pipe carrying a fluid. A circuit is a geometry that creates a field configuration. That configuration stores and transfers energy. Charges move in response, and their motion reshapes the field in return. That is the dance. Now let me show you one of my favorite mental experiments. Imagine you have a battery connected to a bulb with wires. Now imagine the wire is replaced by a pair of parallel metal plates, like a long flat capacitor leading from the battery to the bulb. Would the bulb still light? Surprisingly, yes, under the right conditions, because what matters is not the inside of the wire. What matters is that you provide a path for the field and for the return current some geometry that allows energy flow through the electromagnetic field into the load. This is why you can transmit energy through space with antennas. No electrons from the transmitter travel to the receiver. Fields do. Energy does. Now you may be thinking, but my wires look solid. I don't see fields. Exactly, because fields are invisible, and humans hate invisible things. So we invent the water analogy because we want to imagine something tangible. But physics is not obligated to be tangible. Physics is obligated to be correct. Now here's where it becomes mind-bending. In a steady DC circuit, the electric field inside a perfect conductor would be zero. So how can current flow? The answer is, real conductors are not perfect, and the field exists due to a slight surface charge distribution along the wire. Yes, surface charge, a very tiny amount, but it's enough to create the necessary field to drive current. So when you draw a circuit on paper and you imagine current goes here, you're skipping over the real mechanism, a precise surface charge arrangement that sets up the internal field. We rarely talk about it because it's messy. But it's real. And it's one reason that electricity as electrons flowing is not a satisfying explanation, because it ignores what causes the electrons to drift in the first place. Now I want to simplify all of this into a clean statement you can remember. The electrons are the medium. The field is the message. The energy is carried by the field. The electrons drift to satisfy the field and boundary conditions. That's electricity. Now let's test this picture against your everyday intuition. When you plug in a device and it starts immediately, that's because the field configuration is established quickly across the circuit. The charges in the wires respond. The device receives energy. If you changed the circuit geometry, wire spacing, routing, loops, you would change the electromagnetic field arrangement, and you could change how the circuit behaves at high frequencies. This is why circuit layout matters. This is why engineers obsess over ground planes and return paths. Not because electrons are picky, because fields are. Now I want to address something else people get wrong. They confuse current with voltage. Current is the drift motion of charges. Voltage is potential difference, the energy per unit charge available to move charges. You can have high voltage with almost no current like static electricity. You can have high current with low voltage like a thick, low voltage power supply. The brightness of a bulb depends on power, which is voltage times current. And where does power flow? In the field, around the conductors. So again, not water. Now let's connect this to the thing that really makes brains melt. If energy flows in the space around the wire, then why does insulation matter? Because insulation shapes the field. It affects how the field lines distribute. It changes capacitance. It changes how energy flows and how signals propagate. The space around the wire is not nothing. It is part of the circuit. That's another big surprise. Most people imagine the wire is the circuit, but the circuit includes the surrounding space because the field lives there. This is why electromagnetic interference exists. This is why you can have crosstalk between wires, because fields leak. Now at this point, you can finally ask a deeper question that actually deserves the name physics. Why do charges exist at all? Why do they interact? Why is there a speed limit to changes in electric and magnetic fields? And the answer begins to push us into the structure of reality, itself the same place the speed of light video took us. Because electricity and magnetism are not separate things. They are one thing seen from different frames of motion. Magnetism, in many cases, is what electricity looks like when charges are moving relative to you. And that means the field story is inseparable from relativity. Now, I'm not going to turn this into a full relativity lecture again, but I want you to feel the connection. If changes in electric fields could propagate instantly, you could send signals faster than light, and causality would break. So nature insists that electromagnetic influences propagate at a finite speed. That speed is essentially the speed of light. So the reason your lamp turns on quickly is not because electrons move quickly, it's because electromagnetic influences propagate quickly, but not infinitely. And now you can see why the water analogy is not only wrong, it's dangerously misleading. Because water can push forces through incompressible flow at acoustic speeds in the fluid, but it doesn't capture the geometry and relativity of fields. Electricity is a relativistic field phenomenon, and wires are just one way of guiding it. So what should you imagine when you imagine electricity? Imagine a wire, not as a pipe, but as a corridor full of charges. Imagine a battery, not as a pump, but as a charge separator that sets up a field. Imagine the space around the wires as the real highway where energy flows. Imagine the bulb not as a bucket being filled with electrons, but as a place where drifting charges lose energy through collisions, turning ordered motion into heat and light. If you can hold that picture, electricity stops being magic. It becomes inevitable. Now let me give you one final image. The next time you flip a switch, don't imagine electrons racing from the switch to the bulb. Imagine a change in the field spreading through the circuit like a ripple. And everywhere the ripple passes, charges already present begin to drift. The bulb lights because the field arrives, not the electrons. The electrons were already there. And in a sense, the entire circuit turns on at once, not because it's instantaneous, but because the information spreads so quickly that to you it might as well be. That is the real story. Electricity isn't what you think. It's not a substance. It's not a fluid. It's a field-driven organization of charge motion and a flow of energy through space around conductors. And once you see that, you're ready for the next question that is even more disturbing. If electricity isn't a thing and magnetism isn't a separate thing, then what is actually between two magnets when they pull on each other across empty space? Because whatever it is, it's the same kind of reality as electricity. And that question takes us straight into the thing we try not to talk about. Fields, the invisible structure of space.